Welcome, everybody. Our today's seminar is about the three musketeers of GPU computing. It was all started in 2003 when two research groups independently started to exploit early programmable shader cores in the GPU using OpenGL for the solution of general linear algebra problems. The whole practice was called general purpose computing on GPUs, or GPGPU for short. NVIDIA was the first company who realized the GPGPU potentials and introduced CUDA as a parallel computing platform and API that gave direct access to the GPU for the execution of compute kernels. The first version released in June 2007 and followed by new major releases almost every year. For about 2 years, CUDA was the only player in the world of GPGPU. Then OpenCL version 1 was released in August 2009. It was initially developed by Apple, but later other companies like AMD, Intel, and even NVIDIA joined the effort. And by democratizing GPU computing, OpenCL became the only major alternative to CUDA on that time. Unlike CUDA, OpenCL can target other devices like CPUs and FPGAs in addition to GPUs, and that happens at runtime. And by doing that, heterogeneous computing was coined. Kronos Group is the working body that provisions OpenCL and its new versions. Next in the timeline, we have oneACC, a programming standard that allows annotating C, C++, and Fortran for parallel computing on both CPUs and GPUs. By introduction of version 4, like the way oneACC does, oneAMP, an already existing API for parallel computing on CPUs, started to support targeting other devices like GPUs. In 2014, SYCL started as a higher programming model on top of OpenCL. SYCL can target heterogeneous processors with a single source standard C++. So there is no need for separate kernel file. And finally, we have both AMD and Intel jumping on the bandwagon by introducing their own software stack, ROCm and oneAPI in 2016 and 2019, respectively. While AMD adopted a similar but open source approach to NVIDIA's CUDA, Intel decided to go with SYCL OpenCL. While CUDA started as an API, soon it grew into an ecosystem of compilers, libraries, and various tools in close interaction with each other. And that's also the case for ROCm and oneAPI. Here is a summary of what the latest version of CUDA provides in its ecosystem. In the bottom, you can see the drivers runtimes that CUDA is available. You can see that at the beginning, Mac OS support was there, but not anymore. So now the only drivers are available for Linux and Windows. The programming model supported by CUDA is obviously CUDA and also OpenMP, oneACC, OpenCL, and recently PyCUDA. There are different compilers, mainly C++, C++, and Fortran, and also CUDA version of GDB debugger, NVIDIA Insight, Visual Profiler, and also some performance counters like PapiCUDA. And here is the list of some of the most important libraries, which, for example, linear algebra or cuBLAS and cuSolver are one of those important ones, and also Trust and COP and cuDNN. And there are also some deployment tools like NVIDIA SMI or Data Center GPU Manager that you can use. And here is ROCm ecosystem with the same layout, so you can easily compare them. So for example, you can easily see that ROCm is only available for Linux, this different distribution of Linux, not Windows or Mac OS drivers. And supported programming models are HIP API, oneAPI, and OpenCL. Compilers are mainly HIP-CC and HIP-FC for Fortran, and ROCgdb, ROC and interestingly, starting with ROCm, they support some tools to export CUDA kernels to, for example, HIP. The tool is called Hipify, and the version for Fortran is GPU4. And I lay out the corresponding libraries like the way, so you can find the corresponding libraries for each one here in this table for different ecosystems. And ROCm's SMI is a version like, NVIDIA SMI and ROCm Data Center tool, and etc. And here's the Team Blues ecosystem, oneAPI, again in the same layout. You can see that it's the only one that's available for all major platforms, Linux, Windows, and Mac OS. The programming models supported are SQL, OpenCL, and also OpenMP. There are different compilers and Intel GDB, vTune Profiler, and the tool for exporting CUDA to SQL C2S, which is also called DPCT. And one interesting thing, you see that the oneMKL repeated here several times because all those other libraries like cuBLAS and cuSolver are all included in oneMKL or math kernel library in Intel's ecosystem. In deployment tools, we have CLLS. It's not as informative as, for example, ROCm SMI or NVIDIA SMI, because it doesn't show, for example, the GPUs and temperatures and those other things, but it's something similar. And we have also Intel Cluster Checker and other tools. For CUDA and ROCm programs, the distinction between different GPUs happens at compile time or link time. So to target both platforms, you need two different code bases that produce two distinct executive files. So for example, if you consider here for CUDA, you have a source code in code, for example, .cu, and you use NVCC compiler to turn it into an intermediate representation, which is called PTX, parallel thread execution, or NVPTX. And when this code is supposed to run on the target GPU, it turns into a binary machine code suitable for that, architecture. It is the same exactly for ROCm programs, but the compiler is, for example, HIP-CC, and intermediate representation is LLVM-IR, which is based on LLVM, ecosystem. So, and also alternatively, you can use ROCm to generate two executives from one source code, but that's not possible the other way around because CUDA doesn't support that. For oneAPI SQL OpenCL programs, on the other hand, that distinction happens at runtime. So you have a SQL source code, which is a single source C++. It means that you don't need a separate file for kernel, which is turned into an intermediate representation, which in this case is called Sphere or SphereV, the newer version that also supports Vulkan. And that file or intermediate representation can be consumed by OpenCL ICD or installable client driver or Vulkan ICD. And depending on which ICD is available. It can be run on CPU, GPU, FPGA, and everything. So as a programmer, I have to choose between, if I have to choose between the two, I go with the runtime approach, this one. Why? Because that way I just need to maintain one source producing one executive file that can be run on whatever CPU or GPU that an OpenCL driver is available for it. But as it's usually the case, with great expectations comes great disappointments. As we've seen in the ecosystem slides, both NVIDIA and AMD provide OpenCL driver for their GPUs. So one naturally would expect a SQL program be able to run on NVIDIA as well as AMD GPUs, right? Wrong. And why is that? Because neither NVIDIA's nor AMD's OpenCL implementations have never supported Sphere or Sphere V, and probably never will. But that's not the end of the story. SQL is beginning to be supported on multiple low-level APIs in addition to OpenCL. One particularly interesting one is developed by Scottish software company CodePlay. They named their SQL implementation Compute CPP. And why is that interesting? Not because its name can be confused with Coldplay, the British rock band, one of my favorites, but because Intel bought Codeplay in June 2022. When that happened, some predicted sooner or later, support for targeting NVIDIA and AMD GPUs will be included in the Intel's oneAPI. And here we are. Since December 2022, you can download free plugins from Codeplay site for both NVIDIA and AMD GPUs that work with the latest version of Intel's oneAPI-based toolkit. The version for AMD GPUs is still in beta. And also note, unlike a typical SQL program, you need CUDA and or ROCm toolkits at compile time to target for those platforms. That brings us to the main question that we are supposed to answer in this seminar. Is it the right time to ditch CUDA and ROCm to go only with oneAPI for new projects? Let's deal with it here rather than the end of the seminar. The answer is not now. For sure, there are some advantages. Build once, run anywhere is the most important of them all. But that doesn't outweigh the cons. At least the way it works with Codeplay plugins is more complicated than that. It's like a moving target because with each release, there are lots of breaking changes. It's hard to optimize single code for various architectures. And there are also some portability and performance concerns. So why not go with all of them then? As they say, the more, the merrier, right? Seriously, if you look at it, we already have most of the ingredients. As summarized in this table, the terminology and syntax is close enough between the three. There are even code converters that can convert existing CUDA kernels to heap or SQL. For example, for CUDA to heap, you can use Heapify, both Perl or Clang version, and also GPU Fort for Fortran code. And for CUDA to SQL, as I said, you can use C2S or, and C2S also has another name, is already included in oneAPI-based toolkit, which is DPCT. And if you're interested in source code, it's available under the name Cyclomatic on GitHub. And most of the libraries have corresponding siblings in other ecosystems, as you can see in this slide. But the good thing about this one is that you can see all the corresponding ones along with some, description here to know what they do. And last but not least, the build process can be fully automatized by CMake. For CUDA, support is already included in CMake, but CMake 3.18 is the minimum recommended one. Both ROCm and oneAPI, on the other hand, provide CMake config files for downstream applications. The good thing about this approach is you always get the latest CMake configs included with each new release of the toolkit. So the only missing ingredient turns out to be elbow grease. But don't worry. Here's a framework that makes life a little bit easier for you. One4All is a framework that tries to streamline the process of developing for CUDA, oneAPI, and ROCm simultaneously. It supports 4 target APIs, CUDA, oneAPI, ROCm, still parallel algorithms. All the configurations are automatically done by CMake. It supports unit testing with Catch version 2 or Catch 2, and supports Google Benchmark for benchmarking. 2 sample algorithms are already included. One is a kernel one, and the other one is based on thrust oneDPL. So you have both, a little bit of both work to know how to deal with them. The first algorithm is a generate table. As the name says, generates tables with arbitrary numbers of columns filled with random numbers in defined close range. For example, this I got it from the unit test. It's a table with 8 columns, each column in different range, close range. This one between -10 or -5, for example. And one important thing about this, algorithm is that it doesn't rely on currand, ROCrand, or oneMKL. As we saw, those ecosystems provide the random number generators, but why not using them? The problem is that, first of all, they are not compatible with the C++11 random library interface. And that makes it hard to get the same random numbers using the same seed. So this one is based on PCG family of random number generators. You can find the whole source code and all the things here. I change it in a way that works with different ecosystem or different, for example, for CUDA and oneAPI and ROCm. The good thing about it is that it has exactly the same C++ random library interface. And for those who know, there are 2, approach for parallel random number generation. One is block splitting, and another one is diffra. This one supports block splitting. And the uniform distribution code, on the other hand, is based on TRNG4 library. You can see this, check the source here. The reason that I used it is it's faster than C++11 version and supports both host and device. So the good thing about this whole implementation is that it's using the same seed. You get the exact same random numbers on all platforms, no matter you use CUDA, oneAPI, ROCm, or it's on CPU, GPU, FCPGA, or else. The second algorithm is based on thrust or oneDPL, CUDA thrust or ROCm thrust or oneDPL. It's a scale table, which it scales all the, that table, for example, to another range. For example, -1 and 1. So here is some preliminary benchmark results for you. This is CUDA versus oneAPI on NVIDIA Ampere A100. This is performance for double, and this is for float. If we, for example, consider CUDA 1, then for oneAPI version of generate table, we get about 75% of CUDA performance. And this is for a scale table. They may seem kind of disappointing, but there is a reason behind that. I'll explain it during the live session. So here is the same thing on ROCm, AMD Instinct MI 210 or 210. The situation is a little bit worse here, especially for scale table. And I'll explain it. It's the same thing. And the last one that we have here is actually comparison between NVIDIA A100 and MI 210 AMD, but using their native code. For example, this one is with ROCm and this one is with CUDA. I don't know for why, but generate table double version on ROCm is not, there is something wrong with it. Yeah, I should check to see what's that. But for others, it's more or less the same, considering that the number of streaming multiprocessors are a little bit different, 108 versus 104. But these are some preliminary results. And using the same code, you can also check it yourself on different platforms to see if your results are different or not. Now let's change the gear to the live session. But a word of warning is in order here. The clusters that I'm gonna work on are providing service to other users as well. So it's completely normal that some glitches happen at any time. Hopefully, we wouldn't have any surprises for today. Okay, here I am on Narwhal, and this is the link to the GitHub repository for one4all. All the instructions are included here, and the things that you need, for example, you need CMake version 3.21 or higher to work. And for Cache2 and Google benchmark, there is no need. It tries to find it. If it's installed, it's gonna use it. But if it is not installed, it tries to fetch them from the GitHub and compile them. But if for that one to happen, you need an internet connection working. On the Alliance clusters, you can use this command, modulo CMake, Google benchmark, and Cache2 to have all the necessary things in place. So I'll do that here first. Oh, let me copy and paste better. And then I can, and also, let's do that here. It's better to go to scratch, always is better. And then cd to that folder. Then you can use this command. If you don't mention any target for one4all, I mean the target API like this one, it defaults to STL. So we use the build folder, the name for the build, the full building the STL version. We just choose build. We don't add anything to that. It tries to find the compiler and then the necessary things. For example, TBB. It needs TBB for parallel STL. And once it's done, we can use CMake build command with the build folder and -j to use all the processors. You see that it happens very fast. Why? Because there are only two files, one benchmark, one unit test, and benchmark and Cache2 are already there. So it already found them. There is no need to compile them. Once it's done, to run the unit tests, I can go to build. And remember that usually on our nodes, you should have an allocation or submit a job. But because this one is really small and happens so fast, I just use it like this. I just use C-test to check all the unit tests, which is passed. And then to run the benchmarks, as is mentioned here at the end, I use this command to have all the benchmarks running. Let me make it a little bit bigger here. So the benchmark tries to do it for floating point and also double. For that STL, I just included only float ones, but you can change the code easily. And these are the time, and depending on how long does it take, how long it takes, it's Google benchmark tries to increase the number of iterations to make a sense of it all. And here you can see the bandwidth. I explain more about the bandwidth here. This is a effective bandwidth that is calculated here and shown. But this is the whole procedure that you can run. So this one was using CPUs, but it's not a good thing this way, because CPUs on login node are shared thing, and this benchmark is not representative at all. So it's better to run allocate a node. But I do it for the GPU version rather than CPU, because for the CPU I can switch to our hosted AMD GPU, which is it's not shared. But here, to build the CUDA version, I need to first module load CUDA to have the CUDA toolkit there. And then I can start with this whole thing from here, because we are already, but I should go one folder up to one for all, and then use this one. So here, by specifying that our one for all target API is CUDA, and change the build folder to build-CUDA, we can build for CUDA. Once the configuration done, we can use the same command here. There are some warnings sometimes, and here you can see that depending on, because there is one variable unused, which is tries to find the type of the processor or GPU, but you can ignore that. And once it's done, again the same. You use build CUDA and then test unit test or C test. Oh, yeah, it's failed. Why? Because I tried to run the whole thing where I'm on a login node and I don't have a GPU there. So it complains about no CUDA capable devices there. So what I need to do is salloc, and using 5 minutes, and I use CC debug for account, and asking for use per node 1, and also 4 gigabytes of memory. Hopefully it can allocate. Yeah. And once there, now I can run the whole unit test again. Oh, this one is not the one. Let's have it here. Build CUDA test unit tests. It tries to also say on which device is running, which is obviously a 100. and passed all the tests. And now if I want to use the performance or benchmark, and let's have the targets here. I should put CUDA here. Okay. One important thing is that I changed the whole benchmark thing because Google Benchmark supports to print some more information, and also it supports performance, other performance counters you can add. One thing that I added is that here it also reports the type of the GPU and some information about that. And also one important piece of information, which is peak memory bandwidth or theoretical bandwidth. It calculates it based on the memory's clock. So you can see that the maximum bandwidth or peak memory bandwidth for our GPU is about 1,500 gigabyte per second, which is really huge, but good for us. And if you check here the results, it also tries to calculate the effective bandwidth used by the algorithm. So it shows that, for example, the generate table, which tries to generate random numbers, is not, limited by the bandwidth. The whole crunching thing or whole calculation takes more time, but the is actually utilized about 235 gigabytes of bandwidth. But once we switch to a scale table, it can fully use the whole bandwidth to that. So it's a good situation. Usually, if everything goes right, when you increase the number of things that you process, the bandwidth must be stay more or less the same. And but once you go over the theoretical bandwidth, its performance gonna drop suddenly. So you can check this kind of the things here with these indicators that included in the benchmark. Okay, this one was on Narwhal. We have also one node with AMD GPUs, which are MI 210. I don't think now you have access to that node yet, but I have the access. This is GRA 1339 node. If I do ROCm SMI, you can see there are three MI 210 there. Let me also exit here from my allocation. So here, if you want to do the whole situation is the same. But you should follow the thing in the ROCm thing. You just basically clone the whole thing and then go to one for all. But here you change this, compiler to HipCC, but by this, and mentioning that the target is ROCm. So it uses the HIP compiler, and then you can use CMake. Here, it takes longer because Catch 2 and Google Benchmark are not installed on this node. So it tries to download them and configure them and build them. Now, if I do the building process, it tries to first build Catch 2 and then benchmark, Google Benchmark, and then our unit test and benchmark there. So here you can build for both CPU and also GPU. For running the GPU versions, you just use build ROCm, and the unit test, as always, is like that. But it's good to always check everything is okay, and then perf benchmark, and also having this tabular table. So it also reports this for AMD GPU, and also using the same thing, the peak memory bandwidth and what to utilize and what not. You can see that performance a little bit in, lower than what we've seen for A100, especially for double here, double table generation. But one more thing that I want to show you here is that if we build for the CPU here, let's go with this one. Let's copy and paste. Because this node has 100 and not bad to, oh, okay, this one that I haven't installed TBB here, but I have the result I can show you, no problem. But let's do something else here. This part was easy. The next part that you may want to do that is to build the whole thing for the oneAPI. So here, for example, on Narwhal, let's start with ROCm that we are here. If you want to do that, as I said, you need to have oneAPI and also CodePlay installed. And also you need, for example, CUDA and ROCm if you want to generate a code that can run on all those platforms. Having that combination is really hard. So I also built one Apptainer or Singularity image, which contains oneAPI, CodePlay plugins, CUDA, and also ROCm in one image. That's one behemoth package, which uncompressed, the size of uncompressed one is 45 gigabytes, but fortunately, Apptainer compressed the whole thing, so and reduced it to 15 gigabytes, but if it's still huge. So if you want to build your application, oneAPI application, you need this image. But once the image was the executive built, if you just want to run it, you don't need the whole thing. You can use just the oneAPI and with the CodePlay thing to run. But for building it, you need the whole image. How you can use that? The procedure is like this. You just need Apptainer is already there in this node is already installed. Let me check my history for some versions here. So this one seems good, I think, the last time that I used it. So the things that are here, the dash capital C tries to isolate the whole thing, so we don't have anything from the outside of the image. And we try to, after doing this, we just mount this folder so we can access to our source code. And we should pass -- ROCm because we need the ROCm drivers when we want to run the whole thing on the AMD GPUs. By running this command, I go inside the Apptainer. Now, because it has all the things, we have both SQL ls. If I do SQL ls, I can see that AMD EPIC driver by Intel is there. Also, FPGA emulation platform by Intel. And because it has also the CodePlay plugins, it detected all the three AMD MI210 there. So I can run in them. You can also use other tools, for example, ROCm as well. No, ROCm SMI, because it's already included. But now the good thing is that you can build the whole package using the oneAPI thing. But please note, if you want to generate an OpenCL executive and SQL executive that only runs on OpenCL drivers, you can use only ICPX or Intel compiler. But if you want to target other ones like NVIDIA and AMD, you should use Clang++, already included in the oneAPI toolkit. So because we want to target AMD GPU, we should stick with this version. So here, first, I need to go to folder that I passed to the container, which was one for all here, and then use this command to build the oneAPI version. So you can see that it detected the Intel LLVM compiler. And now that configuration is done, we can build the whole thing. Because the whole building process happened on a system with AMD GPU, by default, the SQL programs target GPUs if you don't mention anything. So because the only GPUs are AMD ones, it automatically runs on that platform. So if I just use build oneAPI and then test unit tests, you can see that it's oneAPI and the device is AMD Instinct, and we passed all the tests. And to run the benchmarks, I just changed this perf to benchmark. I just stop it here. I just wanted to show you that under the oneAPI, there is no easy way to get the clock for the memory. So it doesn't calculate the theoretical bandwidth. But it reports the number of compute units, or for example, this 104, and clock frequency for the whole GPU. And here are the results. Once we build the thing, if I exit from the apptainer and having the executives, if I want to just run it, I can go with this image rather than this one, which only has the oneAPI and also the CodePlay drivers for that. And that's all there is to it. If you want to do the same thing on our clusters, there are some caveats. The first thing is that I put these images on Graham on data share. So if you check data share on Graham, only on Graham, containers folder, you can find these images here. There are two complete one with oneAPI 2023.0 and with CUDA 11, another one which has the latest version, which is oneAPI 2023.1 and CUDA 12, and also ROCm 543. and also the smaller one for the runtime. So if you're interested to do it yourself, you can find these images on the Graham data share under containers folder. And another thing is that if you want to do it on, for example, I demonstrate it on Narwhal. On Narwhal, if I want to do the same thing, let me check my history. Here is one that seems good. Okay, so I'm on my scratch, but this one is not in the data share, it's on my development folder, but I can use that, no problem. And I use this folder to one. One thing that you should notice is that you should pass --env in order to be able to access the NVIDIA drivers on the cluster. So first we have to build it. Oh, and I forgot to load Apptainer here, but no problem. It just asks me which version I want. I just go with the latest version. It shows some warnings about the bind mounts, which is not really important. And once I am there, I can do the same here as well. I can go with this. Oh, I should first go to one for all. And this Apptainer also has the CMake already included, so you don't have to be worried about the CMake. The good thing is that with when you build with this, it has the binary or executive file can be run on all platforms, whether it's AMD GPUs or NVIDIA ones, or Intel CPUs or GPUs. You can use the same, executive to run on those platforms because it's already linked with proper code plating and these things. But you have to use if you don't have all of them, or at least one API, you need to stick to that image, the smaller one, to run it. And after having this, we can build. There are some warnings, but you can ignore it about the CUDA version and those things. They are not really important. And once now here one is finished, I can use SQL ls. You can see there is no NVIDIA mentioned because I am on the login node. So I have to go out and run the thing. But there's a point here. Let me get my history. Okay, I think this one works. So once I'm on GPU node, I can use the same Apptainer command, but I don't have access to it because I don't have a history. Let me see. No, I didn't pass -c. It's better. Oh, let me see. Okay, it's better to use the history again. But why? Yeah, here. Here, this one can work. Obtainer again. Here, if I do SQL ls now, it should mention also the NVIDIA CUDA backend as well. But depending on what I'm going to run, I have to specify where I want it to run. Again, here, maybe it uses the default GPU because the GPU is default. But if not, you can use this one. But the thing is that if you use the 2023.1, the name of the environment variable is oneAPI device selector. But if you use the older version, for example, 2023.0, you should use SQL device filter for that. So to switch to, for example, CUDA or CPU or different platforms. But here, it should work. So I just do build, just change here and then build oneAPI and test unit tests. It should work. But this one is oneAPI now. And also the perf here. You can see the results. Okay, the last thing that I'm going to show you here is that you can also do the whole thing even on your computer. On my computer, I use, this is Windows, and I have WSL2. Having WSL2 is good because my laptop, for example, has both Intel GPU and also NVIDIA GPUs. I've installed both oneAPI under WSL and also ROCm and CUDA. The good thing is that using my computer, I can do the same thing, build the binaries for oneAPI, and then upload that binary to, for example, cluster, and using the smaller version of the Obtainer image, you can run it there if you want. But if you use the Visual Studio Code to do that, one thing that I want to mention here, using the CMake plugin, there are some parameters in CMake. You can, let me also show you here. You can do it also on our clusters, for example, by the build. But if you use CC make, you can change the configuration. For example, for build CUDA, these are the configurations that you need to change. For example, the target API. And if you press T, it switches to the advanced version, that there are some things that you can check. The thing that I wanted to show you, under the Visual Studio Code, you can do the same. If you go to the CMake extension here, you can edit CMake cache here. If you are under oneAPI, which I am now, there are two parameters here. If I search for arc, if you're targeting a ROCm, one thing that you should really notice is that the SQL ROCm arc, I change it to this one. This is for MI 210. For ROCm platform, you have to specify the only one that you need. It doesn't work. At least with the code play one is like that. So you should target the exact same architecture in order to work. So for different GPUs, you should change this one to that. But for SQL CUDA architecture, you can just use the the one that is common. So for example, you can use the SM50, or if you're sure that it's going to run only on 8th version of CUDA or CUDA architecture, you can change this one to SM80, for example. And it supports all those. But for ROCm, you have to change it to exact GPU that you like, which makes it a little bit, this build once and run anywhere a little bit hard. It doesn't work like that here. And I think that brings us to the end of this seminar for today. Thank you.